Now, we will see the application of the first law to the different systems and processes in thermodynamics. First, we see the isolated system. Before that, a quick recap. What is the first law of thermodynamics mathematically? It is du is equal to dq minus dw. Okay, so to an isolated system, we know, or in an isolated system, we know dq is equal to 0 because there is no exchange of heat energy from the surrounding to the system or from the system to the surrounding. That is, there is no exchange of heat energy between system and surrounding. So then du is equal to minus dw. This is purely with respect to system and surrounding. Within the system, of course, the internal energy is equal to minus dw, and dq is also not constant. It is constantly changing. Now, system involving mechanical work only, there we find that du is equal to dq minus p dv. That is the mechanical work, that is expansion work of gas on surrounding or the compression of the surrounding on the system. That is compression of the gas due to work of the surrounding, work by the surrounding on the system. Here we see therefore that du is equal to dq minus p dv. Now comes the isothermal process. In the isothermal process, temperature is constant, so there will be no variation in temperature. If temperature is constant, then there is no variation in internal energy, that is du is equal to 0. Temperature is not equal to 0 here, you see, it is just a constant. Du is equal to 0 and dq is equal to obviously then dw. Why? Because the first law says du is equal to dq minus dw. So, if du is equal to 0, then dq minus dw is equal to 0, or dq is equal to dw, or minus dq is equal to minus dw. Next, we see the isochoric process. In the isochoric process, volume is constant. If volume is constant, then V final minus V initial will be equal to 0, that is dV is equal to 0. Therefore, PdV is equal to 0, and if PdV is equal to 0, then du is equal to dq minus PdV, that is du is equal to dq because PdV is 0. Next, we see in the isobaric process, we have got P is constant. So, if P is constant, nothing is equal to 0 over here. You see, the first law remains as it is, du is equal to dq minus p dv. In the adiabatic process, we have got dq is equal to 0 and du is equal to minus p dv. Why is dq equal to 0? Because there is no exchange of heat between the system and the surrounding. Whatever there is heat inside the surrounding, inside the system, whatever heat is there inside the system, it is going to be used to do the work inside the system. And we have seen the natural processes that occur are the lenticular clouds, or we have also seen the Chinook winds, and how they are actually involving the adiabatic processes in isolated system of air columns rising upwards due to air getting heated up on the earth's surface. Now, we come down to the study of heat capacity, which is so essential in expressing relationships between different thermodynamic quantities. We have seen the amount of heat required to increase the temperature of any given substance on or a system by 1 degree is called the heat capacity of that system or substance. It is denoted by C and it is given by Q upon dt, where dt is the change in temperature, Q is the amount of heat. Now, how much should be the change in temperature? 1 degree. So, then we get the units as calorie for Q and dt is 1 degree and it is going to be per gram, because we have said for how much, for a given mass of substance. If it is going to be 1 gram, then we will have it as specific heat capacity. So the heat required to raise the temperature of 1 gram of substance by 1 degree is called the specific heat capacity, and symbol is denoted as Cs. Molar heat capacity is defined as the heat required to raise the temperature of 1 mole of substance by 1 degree. Symbol is Cm. Moles N is given by given mass upon molar mass. Now the specific heat capacity at constant volume is denoted as Cv. Q is equal to Cv into N delta T. You will wonder from where we are getting this relationship. We have just defined C, that is a specific heat capacity, and it is what the amount of heat required to raise the temperature for 1 gram of substance by 1 degree Celsius. So if you take Cv is equal to Q upon N delta T, then we have it as the molar heat capacity, the molar specific heat capacity, when we have N equal to 1 mole. So from first law, you see delta U is equal to Q minus W, or as we had said, du is equal to dq minus dw. Now delta U is equal to, substitute the value of Q here, Cv N delta T minus P delta V, and if V is constant, delta V is 0. So Cv then becomes equal to delta U upon N delta T. So this part, if it becomes 0, then you are having delta U is equal to Cv N delta T. So Cv is equal to delta U upon N delta T. For a monoatomic ideal gas, from kinetic gas theory we understand U is equal to 3n RT by 2. Substituting in the above equation for Cv, we get Cv is equal to 3R upon 2. What is Cv? Cv is equal to delta U upon N delta T. So substitute the value for delta U. Delta U will be equal to 3nR delta T upon, here you are having N delta T. So that the common factors cancel, and we have Cv is equal to 3R by 2 for monoatomic gases like helium and argon. For diatomic gases, similarly, we have U is equal to F, that is degree of freedom, into nRT upon 2. Now, what do you mean by degree of freedom? Degree of freedom is actually with respect to the molecular motions. A diatomic molecule can have 5 different degrees of freedom, and with respect to its rotational and vibrational motions. So we have here Cv is equal to 5 into R upon 2. Cv is equal to 5R by 2. The gases, for example N2 and O2, they have Cv, that is specific heat capacity, at 5R by 2. Similarly, for triatomic molecules, this degree of freedom is 6, and so Cv becomes equal to 6R by 2, and examples of such gases are NH3 and CO2.